Hello and welcome to this talk on a novice-friendly induction tactic for Lean. I'm Jonas Limperk. I'm a PhD student with Jasmin Blanchette at VU Amsterdam. And this project kind of started with a course that we were teaching. This is a kind of general introduction to interactive theory improving, and we're using the Lean system for this course. So very brief introduction. Lean is a newish dependently typed theory improver. It's very similar to COC in many ways, and like in COC, the primary interface for users, at least when they're building proofs, is tactic based. And in particular in the course we use the induction tactic quite a lot, since we do a bunch of programming languages material, so programming languages, their semantics, that sort of thing, where we have relatively sophisticated arguments by induction. And as we were doing that and teaching that, it occurred to us that the induction tactic of Lean is not really as user-friendly as one might hope. And in particular, it was confusing our students in a number of situations. And to give you an example of what that might look like, here is a well, the goals that induction gives us when we use it on a fairly simple lemma regarding the big step semantics of some toy language. And there's a number of things wrong with these goals. For one, there are 7 goals here, and in fact the first 5 cases are kind of obviously impossible, so the tactic should not even show them to the user. Then, perhaps even more severely, the first case here is impossible to prove with the information that the induction tactic gives us, right? So we are supposed to derive a contradiction here, but all we have in the context are these state things that don't really lead to a contradiction. So this goal is actually unprovable. And then the goals also just don't look very good. So for example, when you look at this hypothesis here, just because of the names that the induction tactic chose, it is kind of hard to see what's going on, at least at a glance here. And all of these problems, and there's a couple more with the default induction tactic in Lean, were definitely confusing our students, and we noticed that we had to spend a fair amount of time teaching the workarounds that experts usually use in order to get around these deficiencies of the default induction tactic. And of course we wanted to use that time more productively to teach people interactive theory improving instead. So I decided to build a new induction tactic, and a lot of this work was just getting up to speed with the state of the art, in particular with COC's dependent induction tactic, which already solves a number of the problems that I've talked about. But it turns out that dependent induction also has some usability issues. And this talk is about these usability issues and how I've solved them, or at least partially addressed them in some cases, with the new induction tactic for Lean. So we're going to talk about 3 things. First, about the handling of complex indices, which is kind of a classic problem for induction tactics. This is where we build on dependent induction, but I further simplify the induction hypothesis that are generated when we are dealing with complex indices. Then we'll talk about the automatic generalization of induction hypothesis. Induction hypotheses that are not general enough are also kind of a classic problem when we're doing proof by induction in ITPs, and so this is an approach to solving that. And then we'll be talking about naming, which is a surprisingly big part of the new tactic. And I'll show you why that's necessary, because if you choose the wrong names, even simple goals can get quite confusing. Alright, let's talk about complex indices. So as I mentioned, this is a problem that's already covered in the literature, but I'll have to kind of repeat the problem and the solution from the literature, because the refinement that I will present kind of builds on that. So here's the problem. Let's take a look at this lemma, which is actually from the course that I talked about. So this is something that our students have to deal with. And this is about a big step semantics of a toy while language, so a toy imperative language. And the statement essentially says that this program here in some arbitrary state S steps to and terminates in some arbitrary state T. But the program that we have here is an infinite loop. It's a while true loop with an arbitrary body. And so hopefully, if our big step semantics are any good, then this statement should be false and we should be able to derive a contradiction. And in order to do that, we do induction on this hypothesis here, so on the derivation of this big step relation, which is defined as an inductive data type that we can do induction on. And as in the previous example, it's actually the same example, we get this rather unfortunate case where we have a contradiction that we have to prove, but in the context we only have these two states which do not lead to a contradiction. So what's the problem here? Why did this happen? Well, the problem has to do with so-called complex indices. We call a term complex if it is not merely a variable. Right? So t here is not complex, it's just a variable, but this thing here, this tuple, is complex. It is not just a variable. And the problem comes when we have such complex terms in index positions. Right? So this big step arrow here is defined as an inductive data type with two indices, like relations usually are. For those coming from other formal systems, indices are kind of a specific thing in dependent type theory. See the paper for details, but essentially the dependent type theory makes a distinction between different kinds of arguments of inductive data types, and indices are one of these kinds. Right, and so here both arguments to the big step relation are indices, and this index here is complex, and so then we get into trouble. And we get into trouble because the induction tactic essentially treats complex indices as if they weren't there. So it acts as if this whole thing here was just an arbitrary variable. It throws away the entire information that we have here, that this is a while true loop. And you know, this works for some proofs actually, but most of the time you get into this unfortunate situation where, because we've thrown so much information away, the goals that we get actually become unprovable. Okay, so how do we deal with this? Well, here's the classic solution due to McBride in this elimination with a motive paper early 2000s. Since then there have also been some refinements to the method, but they are not really relevant for our context. Well, essentially the idea is this. So here we have the goal again. This is the hypothesis that we want to do induction on. And now we use a kind of trick. And the trick is this. We replace this complex index here by a new variable called I, and I is of type program cross state because that's the type of this thing as well. And then we constrain this variable with an equation that we add to the target down here. Right? So we say, okay, the complex index is replaced by an arbitrary index, but oh wait, the arbitrary index is actually constrained to be exactly what we had up here. So these goals are trivially equivalent. However, they are nicer for the induction tactic, right? Because now there are no complex indexes inside here. And so the induction tactic can actually work its magic. And this time we get some more information out of the induction tactic because of this transformation. And in particular, it gives us down here, okay, in the skip case, this is the case of the big step semantics that applies to the skip constructor of our language. So this is just a no-op operation. It's just one of the constructors of our abstract syntax tree. And now we get an equation that says, oh, okay, this while loop is equal to the skip program. and that is wrong. These are different constructors, though that's kind of just trivially false. And therefore, if we eliminate this equation, we can actually prove this case now, because we have some contradicting evidence in the context here. And tactics based on this method, in particular Cox-dependent induction, actually do this automatically. So they post-process these equations here and essentially do first-order unification of the left-hand side and the right-hand side. And when they encounter this sort of case, where there's two different constructors on the two sides, then they dispatch the goal immediately. So the user actually never gets to see this case. Okay, so far so good. That's what the literature does. However, there is one problem that remains with this method, and this is the induction hypothesis that it generates. So here's a typical induction hypothesis, and you'll notice that we have this equation here. And this is very unfortunate, especially in an education context, because like the goal that we applied induction on didn't have any equations. The goal that we get also doesn't have any equations, because they've been eliminated by this first order unification mechanism most of the time. But in the induction hypothesis, we have these equations, and I'm sure any beginner is going to be confused about what this equation does here. And that's kind of unfortunate, obviously. And also, this equation is really quite useless if you look at it, right? We quantify over this s prime and little s prime over here, but then the equation constrains these s prime and little s prime such that they can only take one value, right? This s prime can only be s, and this little s prime can only be t. So that is something that we can probably do something about. And this situation occurs often enough in practice that we thought it would be worthwhile to do a post-processing step for the induction hypothesis as well. And well, what we do is very simple, really. First, we eliminate these things here, which are induction tactic edits. We're going to eliminate these variables and replace them with meta variables throughout the whole induction hypothesis. And then we run first order unification again, right? So we unify the left-hand side of this equation with the right-hand side of this equation. And in this case, obviously, unification will return a substitution, assigning this meta variable the s and this meta variable the t. And so then we apply the substitution, and we get an equation where both sides are trivially equal. And when we get such equations, we just remove them from the induction hypothesis because they're trivial. And so this is the induction hypothesis that we get at the end of the day, which I would say is quite a bit less confusing than the induction hypothesis that we had before. And of course, if we have multiple equations, right, we can have multiple complex indices, so then we get multiple equations. In that case, we just kind of iterate this process, right? So we replace all these variables, and then we move through each equation and unify them and see what happens. Now, unfortunately, this process is not really complete in any sense. So there are situations also in practice where we have equations that we can't so easily remove, and in those cases, well, we leave them in the induction hypothesis, and people have to deal with them, unfortunately. But in many practical cases, we can actually simplify the equations away, and then we get the induction hypothesis that you would want and that you would expect to get on paper. Moving on to the second problem that our new induction tactic addresses, which is overly specific induction hypothesis. And this is a problem that every beginner runs into sooner or later. It's a classic kind of trap that these induction tactics set for their users. And so this is something that we thought we should do something about. So here's the problem, illustrated with an example that I stole from Benjamin Pierce's Software Foundations. So we have this very simple little injectivity lemma here, where we have to prove, okay, n plus n equals m plus n. If that's the case, then n equals m. seems simple enough, and so the unsuspecting beginner will introduce n and m, because that's what you usually do with all quantified variables, and then they'll do induction on n, and then they will get surprised, because here we have a situation where we know that n plus 2 equals m plus m, but our induction hypothesis requires us to show that n plus n equals m plus m, which is definitely not the case. So what gives? This is a very confusing situation, because as a beginner you don't necessarily realize what's going on here. You don't realize at first that this is unprovable. You try a couple of things, and then maybe at some point you realize, okay, this cannot actually be proven, but you don't really know why it cannot be proven. And the answer, of course, is to generalize the induction hypothesis. Right, so here in this proof we essentially fixed a particular m when we did induction. Well, what we should do is we should let m vary over all natural numbers. And if we do that, and the existing induction tactics all allow us to do this with special syntax, or we can also do it manually quite easily, this is not really a problem, then we get this more general induction hypothesis, where we say, okay, for all possible m, if we have n plus n equals m plus m, then n equals m. And so now we can instantiate this m, not with this m down here, but with a different term, and then we can apply the induction hypothesis and eventually close the goal after some more manipulations. So, as I said, the problem here is not that it would be impossible to do this generalization. It's quite easy, but the problem is that you have to recognize that you need to do the generalization in the first place. And we didn't really want our students to have to deal with this, and this is why we thought, okay, what if we generated the most general induction hypothesis from the get-go? Because these induction tactics kind of generate the most specific induction hypothesis possible in some sense. But what we want to do is we essentially want to perform this generalization here automatically without the user even having to think about it. What do we do in order to make this happen? To a first approximation, this is extremely simple. We just revert all the hypotheses that we can. So in this case, we can really only revert m here before we do induction on n. And then this reverting leads to a more general induction hypothesis. However, there is one corner case that we need to be careful of. And the corner case is this. So suppose we have this goal here, and we want to prove this commutativity of addition by induction, but we also have this x hanging around in the context here. Now you might say, okay, well, isn't this a super synthetic example? What is this x doing here? Yes, it's a synthetic example, but it is representative of actual practical use, and we've had such cases in the course. Because sometimes, for example, you do a longer proof and you want to prove some sublemma by induction in line. But then you have a bunch of stuff in the context that doesn't necessarily have anything to do with the lemma that you want to prove, because the lemma only involves kind of the parts of your original problem. And then you can have the situation that you have some x hanging around here that doesn't really have to do anything with anything else. But what happens now when we do the naive generalize everything approach is we get an induction hypothesis like this, which generalizes over the x. But this is obviously useless. I mean, we can still instantiate the induction hypothesis with the x that we have here. This is not harmful in a strict sense, but it's certainly not useful either. And so, in order to prevent this problem, I've devised some criteria that approximate, essentially just a heuristic to tell whether a generalization is useful or not. And the heuristic is very simple, at least the intuition. The technical details are a bit more complex than what I make them out here, but you'll have to read the paper for that. But the intuition is very simple. So essentially, in order to generalize a hypothesis, there are two conditions, and if either of them is fulfilled, then we generalize. So the first condition is if there is a connection with the target, then we generalize. What this means is, so here we have this hypothesis M that could potentially be generalized, and this hypothesis also appears in the target. And so generalizing this sort of hypothesis is often very useful, and indeed is kind of the primary purpose of this tactic a lot of the time. And so if we have this connection between the hypothesis and the target, then we always generalize. And the other connection is a tiny bit more subtle. This is a connection with the hypothesis that is to be eliminated. So here's another example where we have this n greater than or equal, and here we assume that the greater than or equal is defined as an inductive data type. You can also define it in other ways, of course. But you can also define it as an inductive data type, and in this case we can perform induction on this statement over here. And now we have this hypothesis H2, and the question is, should we generalize or not? Obviously H2 does not appear in the target, so the first condition doesn't apply, but H2 involves a term that also appears in H1. And more specifically, H2 involves something that appears as an index in H1. And these terms are usually interesting because when we do induction on this statement here, we are likely to learn something about the indices of this greater than or equal relation. And we're likely to learn something about this n. And in that case, it is also likely that we would like to make use of this information here applied to the new value of n. And so in this situation, it also makes sense to generalize. And so we generalize this H2 hypothesis and make it an implication in the target. Then we perform induction. And then, for example, in the zero case of this induction, so when n equals 0, this information is propagated into this H2 hypothesis, and then we have 0 not equal to 0, and so we can discharge this case. And if we had not generalized H2, then that wouldn't be the case, and we would get kind of stuck with this case, or we'd have to prove it otherwise. The third area where our induction tactic improves on existing tactics is naming. And you would be forgiven for saying, okay, well, how can that be a big deal? But let me show you. So here's an example, a lemma that we let our students prove in the course as well, or I think at least very similar lemmas. So it's about the transitive closure of a relation R, called TCR here. And what the lemma is saying is, okay, if the transitive closure relates A and B, and it relates B and C, then it also relates A and C. In other words, the transitive closure is actually transitive, which is non-trivial with the particular encoding of the transitive closure that we're talking about here. Now, we'd like to prove this by induction on this hypothesis, and Lean's induction tactic gives us this goal here, which I think you'll agree is rather a mouthful. And the problem here is not so much the goal itself, it's really the names that the induction tactic shows. So these H1 prefixes are making it very hard to see what's going on, and there are other problems as well. So here we have some A and B. These don't really appear in the goal anymore, so it's not clear why they're still here. And we also have lost the connection between this A and B that we had here and whatever is going on in this goal, right? Our goal was to prove that A and C are related, but here we have this H1x, so where's that coming from? And at least as a beginner, I wouldn't blame you if you were confused by this goal and wouldn't know what's going on, like why is this goal what it is when we perform induction on this hypothesis here. In fairness, Coq does a lot better. It at least doesn't have these H1 prefixes, so the goal is visually a lot more pleasing. It also removes the A and B here, but it still has this problem that we have this X, Y, Z, which are not in the original goal, and we have the target changed, AC versus XC. It's still not clear what's going on. And, well, the new induction tactic solves this problem. So there are two differences. First, we have auto generalization kicking in here. So we've got this additional quantification over C, but more importantly, we still have A, B, and C in the goal. And the target is still A and C are related. And then we also have this new Y, but that's fine. That's actually a new thing that we are introducing. Okay, how do we do that? Well, essentially, we have a new naming rule. So the way the naming works is there are a bunch of naming rules that are kind of tried in sequence, and when the first that applies is taken. And many of these naming rules already appear in existing tactics, so there's not really that much new here. But this particular rule is new and I think is somewhat relevant. So essentially, the problem that we had is, okay, we have this A and B here in the goal. How do we connect it to this X and Y? And to see how, we have to know where these X and Y and Z come from. And they come from this constructor here, which is the constructor that corresponds to this particular case of the induction. And essentially what happens is that these arguments of the constructor, X, Y, Z, are just added to the goal by the induction tactic. And this is where they come from. And then we lose the connection to A and B. How do we restore this connection? Well, essentially by noticing that the X here is associated with the first index of TC. Right, so the first argument of TC, in other words, because it is the only constructor argument that appears in this index. And similarly for Z, it is associated with the second index. And then we, when we have this association, we notice that up here, the first index is instantiated with A, and so we should really name this X here A, and then we should name the Z Y. And then what remains is the Y. This is in the goal, but that's fine because that's not associated with anything that we had in the goal previously. And so we can choose kind of an arbitrary name. So this solves the problem, makes the goal just a little bit better, makes it just a little bit clearer what's going on. There is one additional condition, which is kind of a type-based restriction of this principle, but I'm not going to go into this in this talk. Again, please read the paper for all the details. We also have one other naming rule that I think is kind of interesting because it implements type-based naming in a way that at least I haven't seen anywhere previously. This kind of makes use of the unique metaprogramming features of Lean. So essentially in Lean, we can associate a type called alpha with a list of names by way of a type class that we will call variable names. And this name type here is the type of names that Lean operates on internally. So these are names that you can give to a variable or something. And this type class now makes it possible to associate a type with variable names. And so to say, for example, okay, if we have a variable of type natural number and we don't have any more appropriate name for this variable, then you can choose between the names N, M, or O, depending on which one of these is already taken. And if you have something of type prop that needs to be named, you can name it PQR, for example. And we can also do some cute things with this. So for example, here the instances for lists is kind of interesting. So here if we associate the name alpha with some typical variable names, then we can get the typical variable names of lists of alpha by saying, okay, take the typical names for alpha and just append an S to each. So a list of natural numbers would be called NS, MS, or OS, depending on which of these are already used. So this is kind of a nice way to do this, I think. And it is also very convenient for users, particularly because you can overwrite these instances quite easily. In Lean, you can define a different instance that has a higher priority. And so if you really dislike the names that I've chosen for propositions here, you can just define your own prop instance, and then you'll get different variable names. And again, this mechanism only kicks in if none of the other naming rules, like I've shown you one, but there are several others. If none of these kick in, then we just choose kind of a default name based on this mechanism here. So in summary, I have talked about 3 things that kind of make the induction tactic just a little bit better, each one of them. The first was the simplification of induction hypothesis when we're dealing with complex indices. The second was this auto-generalization mechanism, so that our users don't have to worry about overly specific induction hypothesis anymore. And the third was naming, and I've shown particularly index and type-based naming. There is also another section in the paper which I didn't talk about at all, so let me just do a little ad here at the end of the talk. In the paper you'll also find an evaluation of Lean 3's metaprogramming framework, because this tactic is kind of a fairly substantial example of metaprogramming in Lean, and so I thought it would be useful to write up my experiences and particularly some difficulties that I encountered when metaprogramming in Lean. Luckily, or unluckily, depending on who you are, this section is already out of date because the paper is before the paper is even published, because a few days ago the first pre-release version of Lean 4 was released, and it kind of changed the metaprogramming framework in a lot of ways, and in particular I'm very happy to report that it already addresses some of the issues that I identified with Lean 3's metaprogramming framework. Some of them also remain, but I'm sure that they'll get fixed as well. So a bit unfortunate for the paper, but fortunate for you prospective users of Lean 4. Alright, I hope you enjoyed this talk and have a nice evening.